Good evening, everybody. I would kindly like to request that one of you just confirms if you can hear me just fine. My microphone, my external microphone is fading me again, so I'm using my okay. Thank you for the thumbs up. You know, colleagues, I have no idea how to get through to you. You know, I have no idea how to get through to you because today is the 30th of August, right? And you know, I was marking the quizzes. I started marking the quizzes yesterday, and so usually when I start marking, it's when I'll share the model solutions, if you will. So again, those are model solutions. I'm not saying that the solution is supposed to be exactly like that. And what you notice in most of the model solutions is I mostly will do the simplest possible. I'll come up with the simplest possible solution, right? Probably a solution that most of you would find themselves thinking about, you know. But you know, when I started going through the scripts here, you know, this will sound like a joke here, right? But you know, I sat there and I was asking myself, you know, how did these people, right, find themselves in fourth year, right? And I'm being serious here, you know, because some of the things you people are writing here, it's almost like you've just started learning how to program here, right? It's quite sad, really. And I'm saying this because I'm trying to figure out how best I can. Don't mind what I'm doing on the screen here. I'm just updating my slides. I've decided to dumb them down a little bit here because perhaps the high-level stuff I've been including in the slides are not very helpful. So I spent the last couple of minutes here. Instead of doing my laundry, I was updating the slides. You know, I'm supposed to be doing my laundry here, but I had to update these slides because my thinking is that maybe people will be able to follow through with these things if I dumb them down a little bit, right? I'm asking you a simple question where you're required to just show me the output, right? Of like get dummies or one hot encoder. And you are failing to tell me that. I mean, really, honestly speaking, how many times have we gone through these examples, right? Not only that, really, if you look at the notebooks I've provided to you, right? Those things are in there. I record my lectures, right? All the code examples that I give are in my lectures. So I don't know, right? I don't know what's going on here. If you're having problems and you feel I can help you with whatever problems you're having, my office is 515. I know I'm very far from the School of Natural Sciences, but come to the School of Education, Bridge Building, room 515, you will find me there, right? You know, come and see me. I've given you details of my office hours so that I help, right? What I'm potentially going to do, I haven't really confirmed this yet, but if you wish, if you're having trouble, tomorrow from right after my class, I'm going to be online. I'll schedule an online session. I hope I don't forget here. I'm going to be online tomorrow. Let's come through with whatever problem you have, because I mean, I have class between 5 and 6, between 17 and 18 hours. So I'm going to be online from 18:30 to 19 hours. Just log in. In fact, I'm going to do it right now. I'm going to call this a query session or something. Log in if you want to, and come and tell me what the problem is. If you want to come and see me in person or something, that's Monday, by the way, not tomorrow, because tomorrow we have another class. But if you want to come and see me in person, just let me know when you want to come through, right? So that I can help explain or help guide you, right? I'm worried that we're only remaining with, I'm going to put this at 6:30. I'm worried that we're only remaining with very little time here. you know, and some of the things that you should see these scripts, right? I have some of these in front of me here, right? um, I don't know. I don't know. Anyway, so just to let you know also that we have class tomorrow. I mentioned that we're going to have class because, you know, I think we missed, is it a session or two or something when I was attending that workshop, right? And that conference or something. And then tomorrow, I mean, yesterday we didn't have class because you had elections or something like that. There was that email from the DVC here, crazy stuff happening. No classes because the elections or something. So I have class tomorrow, 18 hours, right? And that's that. Anyway, so we're going to continue our discussion of this lecture series. I thought I saw a hand up, but it's gone now. We're going to continue with our discussion of this lecture series, and a reminder that we're looking at data transformation. I'm hoping that, I'm hoping, my plan is for us to wrap up this discussion tomorrow, okay, so that we can start looking at lecture series number 5, where we begin to look at how we go about implementing these things. The other thing I mentioned to the course rep, Ms. Mlela, to be specific, because she had sent me, I think Chela is busy with, there's an event that he's attending apparently, Zamrin Week, to reassuring some of you that attend those important events. Yeah, so my plan is for us to finalize this discussion of lecture series number 4 tomorrow, so that come next week we start our discussion on lecture series number 5, where we start looking at modeling, the modeling phase of the CRISP-DM methodology. All right, so on with it. A reminder, you know, some of these things, I don't know what's going on here, where somebody tells you a solution, is talking about a solution in class, and you're still failing, right? But anyways, a reminder that we started going through this heuristic homework for you. Implement. The implementation is understand the implementation of the manual implementation of the bag of words model, right? It's a 4-step procedure where you are looping through all the documents in your corpus for you to, first of all, make or create your vocabulary. In essence, a list of unique words that appear in all of your documents. After you do that, you create word vectors for each document, right? So in essence, you create for each document a vector that showcases the frequency of each of the unique words in your vocabulary, right? That's it. That's what you're doing in this heuristic. I spent a great deal of time. In fact, I feel bad because in the last lecture, we spent a whole lecture me trying to explain this, because I have a sneaking suspicion I'm failing to get through to most of you. So we had a discussion, I had a series of examples. I walked us through this. At some point, I was even using an example of I am Chela or something. I'm 4th year and all those things, if you remember. And I was showcasing to you how you go about counting the frequencies, right? I hope you now understand why this embedding is called a bag of words, right? It's a bag of words model. We looked at the advantages, right? It's simple to implement, works quite well for small to medium-sized data sets. I remember one of you came to see me, but how do we know what is small, what is medium, right? And my response was that you'd have to experimentally determine this, but what they're telling you is that if you have like a data set similar to what you guys are working on, count vectorize, I mean, the bag of weights model works just fine for all of your use cases, actually. So in fact, at the end of this class, I expect all of you to finalize the data preparation checkpoint. I told Mlela that I was going to extend that checkpoint because we need to finish this discussion. It would be unfair for me to expect you to work towards that checkpoint when we haven't finalized this. So in other words, what I'm saying is, if you want, you can use the other techniques here, like TF-IDF, you know, continuous bag of words model. But what we're telling you is that the bag of words model is going to work just fine for all the projects, topics that you're working on. Anyways, So we see here that some disadvantages that we highlighted. And again, I gave you another example from our students at risk of failing dataset. Now, see the implementation in the notebook. Now, sorry to break it to you, but it turns out that you do not need to manually, you don't necessarily need to manually implement the bag of words model. It turns out that it's available by default, right? It comes bundled with scikit-learn or scikit-learn, so you see exactly how we go about using count vectorizer. Create an instance of count vectorize, and then we use that to vectorize our corpus. And in fact, you do the vectorization in one single step. However, it becomes important for us to understand other important parameters associated with count vectorizer. So we see here that there's a problem with the manual implementation that we're just from looking at. If you were to write this from scratch, it would be time consuming. In fact, you'd have to do this for every potential problem that you'd be working on that requires you to use this sort of embeddings, right? But also, there becomes a need, right, for you to handle certain edge cases. And in fact, important things like how to ensure that your solution is optimal in terms of the consumption of compute resources. So you soon see here that when you're using count vectorizer, it becomes relatively easy for you to do this. In fact, the other interesting thing about count vectorizer is that you can feed it parameters that will automatically remove stop words for you, right? So you wouldn't necessarily have to, in fact, even the case forwarding is done on your behalf, you wouldn't necessarily have to do those preprocessing steps manually as well. Anyway, so we see here that the solution using our scikit-learn library is so-called count vectorizer. It's a built-in class within scikit-learn, which enables us to implement the bag of words model. All right. Now, again, what you will notice when we start doing the fit and the transform is that the API is actually consistent, right? Consistent with these other instances that we've worked with, like for instance, one hot encoder, right, or the ordinal encoder. It's more or less like it's a consistent API that makes it a lot easier for us to understand how scikit-learn works, or rather to scale up as we're working with other instances within scikit-learn. And of course, it provides us with extremely powerful parameters, which will enable us to customize our count vectorizer, right, to suit a specific problem that we'll be working on. Anyways, just to mention that the examples I'm going to be using are the examples from the students at risk of failing dataset. Now, the first thing we have got to do is for us to use count vectorizer is we have got to import it from scikit-learn. And to be specific, the way import it is, look at the second line here, from sklearn.featureextraction.text, we import count vectorizer. I hope this makes sense. We do the usual things, right? Because we're interested in, I'm trying to make an example here, because we're interested in analyzing entries that are not now. You notice here that I'm dropping, right? All those things that are NA. Again, I'm using a context switch here. We'll get back to this. If we have our student database like this, what we are saying is that our students at risk of learning dataset like this. What we are saying is that for us to use count vectorizer, right, we have got to say from sklearn.featureextraction.text, we say, in fact, if you just say from here, if you say dot, you will find count vectorizer here, right? If you notice. Something else we're going to look at is TF-IDF vectorizer, which is here. All right. Hope this makes making sense here. So what we're saying is that we say from sklearn.featureextraction.text, we say import count vectorizer. Vectorizer uses American English, is it? There's no S here, it's a Z at the end. Right? Okay. So we're saying that for us to use count vectorize, obviously we've got to prepare our corpus. We are working with corpus, right? It's text, we're working with the corpus. We prepare our corpus like that. just showcasing some sample entries from our corpus here. You can ignore this stage. In essence, what I'm showcasing to you to say, it's examples like these. Like this. The text, the documents that you're seeing here are gotten from here, right? In fact, yeah, so like this, right? These are the sample documents I have here, okay? And then again, this code is just printing out the sample responses here from this list that I've created. You can ignore this. Yeah, so what we see here is after we import count vectorizer, right, from sklearn.featureextraction.text import count vectorizer, we have got to create an instance of count vectorizer. Now, this is the simplest possible instance. You notice count vectorizer here, var underscore vectorizer. This is a variable that's going to hold our vectorizer. Doesn't have any parameters, right? It's like we're using just the default, the default values of different sort of parameters. And there's a whole slew of parameters. At your own time, for you to appreciate these parameters, we're not going to discuss all the parameters, but at your own time, for you to appreciate these parameters, what you must do is you must go to the documentation. But where is it now? You must go to the documentation. Yep, there we go. You must go to the documentation, right? Like here. Oh, this is TF-IDF, and go to count vectorizer. Right? All of these are the possible parameters associated with count vectorizer. Now, what you'll notice here, and I'll talk about some of these parameters just now, but you'll notice that their default values, these are keyworded parameters, so their default values are already assigned to them. Like for instance, by default, when you use count vectorizer, case forwarding is going to apply lower casing. Okay? I'm just going to share this with you. You can Google it up, but I'm just going to share it with you in the in-call messages in the event that you want to look at that. So we create an instance of count vectorizer. Again, you notice here that we are assigning count vectorizer a variable because there are a couple of other things that we're going to do to this variable, right? Like we'll be using the same variable to get the features, our vocabulary, for instance. You know, we'll be using this same variable for us to build a data frame which we are going to then stitch to the original data frame if you need to do that. So we create an instance of count vectorizer. I'm just calling it var count vectorizer is equal to count vectorizer, right? Like that. In fact, you can even check the type. Just go to type count vectorizer, and this thing will show you say you've created an instance of count vectorizer. Okay? Afterwards, we then fit and transform the corpus. We fit the corpus so that we learn, right, the vocabulary. We transform so that we vectorize, we create the frequencies. But the preference is you do this in one step. Right? Instead of doing a fit followed by a transform, we do a fit transform in essence. Scikit-learn is flexible like that, right? You can do this in two steps, or you can do it in one step. The preference is always one step, right? It's a lot easier like that. So if you notice in step number 2, what we are saying is that we use the var, this variable I've created, var count.vectorizer, right? And then I say dot, I access the fit transform. You notice it says fit, there's also transform. So I do the fit transform, right? Fit transform, the parameter it expects is your corpus. If that makes sense. Our corpus in this particular case, our corpus is this, is it? So I'm just going to say var student, so that it's not confusing. I'll call this var student corpus is equal to that, right? Our var student corpus is essentially a series, is it? It's a series of the column that has the motivations, the text, open-ended text. Right? Using this open-ended text, I'm saying I am going to use the vectorizer to call dot fit underbar transform. Fit transform expects input, right? In this particular case, is going to be the student corpus. right? Now, what you immediately notice here is some of the things that I've mentioned in the past, right? Like it's telling you that what has been generated is like a compressed sparse matrix here, right? Which has 1,726 stored elements, and the shape is such that there are 273 observations, and guess what? 523 columns, is it? So in other words, what this thing is telling us is that when I fit and transform, when I fit this, the vocabulary, the unique words that I have, or that you have in your corpus, are 523. Now, because we're going to have to play around with this sparse matrix, like for instance, we're going to have to unbundle it so that it's dense and we stitch it back to the original data frame. What we are going to have to do is make sure that this sparse matrix is stored in a variable. So what I'm going to do is I'm going to say var count vectorizer underbar data is going to be equal to this vectorizer.fit transform. Okay, so that in essence, I'm going to hold this thing here that is outputted as a result into a variable that I can then play around with. Observe, if I do a type, using a type built-in, and I check the data type of this type, not TP type. If I do this, it's telling me that it's a sparse matrix. In fact, if I just output a variable, it'll be the same as what I had outputted before. So we fit it. Now, when you fit it, right, it turns out that there's a couple of interesting things that are going to pop up. Like for instance, you can check the vectorizer here and spit out the vocabulary in essence, and the order. I think the order is maintained, right? So at this thing, the get feature names out function does, notice I'm not running this on the sparse matrix, but I'm running this on the vectorizer. In other words, I'm running this on this, on the vectorizer itself, right? So if I say vectorizer.get feature names out, guess what? It's giving me, right, an array of words, is it? 10, 12, 2017, 2030, 5 years, 8th, actually, advancements, almost, all, and all those things. Now, here's the thing. If I count, if I do a len on this, it's showing me that there are a total of 523 words, right? If I count the number of features, 523 words. Guess what? If I spit out the sparse matrix, which is var underbar count vectorize underbar data, it's telling me that my compressed sparse row sparse matrix has a shape which has 273 observations and 523 columns. So in other words, the way this sparse matrix has been created is in such a way that it's a long vector which comprises of these 523 words lined up, right? Column by column. So in essence, I've created a data structure that has 523 columns with corresponding frequencies for each word. I don't know if this is making sense here. So true to that, actually, I don't know if I'm getting ahead of myself here, but what I can do here is I can, the way you unbundle a sparse matrix is you can use the toArray method, right? If I do the toArray method, it's going to generate a 2D, well, it's going to generate a multi-dimensional vector that shows me the frequencies for each of these 523 columns. So for each of the 273 observations, for each observation is telling me to say this word here. I'm going to copy this out. When I use the toArray method, what this thing is telling me is that for each of these 523 words, for this word, because I know it's numbers, but this word 10, for the first document, there is no 10, which is why it's a 0. How about 1, 2? There's nothing in 1, 2. And true to that, right? If you unbundle this, if I say get this array and I want to get the very first document like this, it's going to stretch out. It's going to stretch out all of the frequencies associated with all of the words. And if I start counting here, 1, 2, 3, 4, 5, 6, word number 7 occurs in the very first document. I hope this order is meaning that 1, 2, 3, 4, 5, 6, 7. So the word able appears in the very first document. And true to that, you can check, right? You can say, I'm going to get this student database and then get. Now, where's the survey here? I'm going to get the survey responses like this, but it's also in corpus, but I'm going to do this anyway. If I get this series and I get the very first document, right? The document itself, the sentence is going to have the word able, right? Am interested to know how computers function and be able to interact with different computers without having any challenges. And notice if you count here in this particular document, the word able appears once, which is why, maybe if I copy this, it will be a lot easier. Which is why, if I get this array like so, and then I open up a new tab here, right? This is able. And if I start counting, right? This is 1, 2, 3, 4, 5, 6, 7th word. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. The 27th word in the vocabulary appears in the first document. So if we check the 27th word, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I don't know if it's the 27th word here. I have to start to count. This is horrible, right? Isn't there a way of counting here? This is like, I don't know how to count here. 2, 4, 6, 8, 2, but we can count here. 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this is 22, 22, 23, 24, 25, 26, 27, 28. Oh, it's 28. So the 28th word appears in the first document, right? 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So what we're saying is that the word M appears in the first document. And true to that, guess what? M is the very first word. And I was looking at this, is you can say, well, I want to check something else here. I want to check I'm going to check the second document or the very last document, perhaps. I don't know if it's a good idea here. Very first document. The very first document is an interesting case, right? Almost all of these things are 0. What does that mean, by the way? Any takers? Why is it that what could be the reason? The last document in our corpus, all the frequencies are 0. Why is this the case? I can't see a 1 here or more than 1. Anybody?
Because the document is empty.
Beautiful. Thank you very much. And I can't see who that is here, but because the document is empty, beautiful stuff. If you check this, you'll notice here that I get an error actually because the thing is let me see here. I don't know why this thing is I'm going to just do a tail or something. Just going to do this here, -1. Right? It's empty if you notice. If I do an iLook, it's empty. There's nothing there. Yeah, you probably want to play around with this so that you understand, right? So document is empty like that. Anyways, I'll get back to the two array and stuff so that it makes sense. I wanted to showcase that. So we fit and transform in one line of code so that we learn the vocabulary and so that we vectorize our documents. And what you notice, something interesting here is no looping here, right? Everything is done in one go. So you're just feeding it a corpus. The input is a corpus here. The parameter is a corpus, right? Now, some key terms here. A vectorizer, right? The count vectorizer. This is the object that converts text to numbers. We import it from sklearn, right? Dot feature extraction dot text. And then the fit and transform will help us learn the vocabulary, which is why we have the get feature names out, spitting out all the 523 terms in our vocabulary. Guys, look at this. Look at this. I'm going to come here. I thought about this here. I'm going to come here and get that other document. Huh? This, the unza dspace. If I come here and I say var unza ir is equal to pd.read csv sep is equal to this, and if I do this, if I create, I don't want to mess up the previous vectorizer, but if I create the dspace vectorizer, if I say this is equal to count vectorizer like this, and if I say v dspace, because when you fit and transform, right, it's going to be attached to the corpus you're working with, so I don't want to mess up what we created here. If I do this and I do a fit transform, what I want to do is I want to transform different pieces of text. If you remember our dspace dataset, it has a abstracts, is it? Which are described by, they're represented by this description, volume or series, right? These. Now, guess what? If I do a fit and transform on this, if I come here and I say, I've created my vectorizer, right? But I'm going to say underbar data is equal to var dspace vectorizer dot fit transform. I'm going to fit transform var this. I want to fit transform unza IR, which has description, like so. Now, the reason this is fading, by the way, is because the dspace IR, it's crazy like that. The unza IR here has got to, I've got to replace this description. I'm going to have to say do FUNA, right? There are some null values here. In fact, I'll just say missing data like this. And then I'll say in place is equal to true, right? So that it's preserved like this. If I learn the vocabulary, it's going to take a while. It's a lot of documents here. Get this. If now I check, right, this sparse matrix, surprise, surprise, right? Our student at risk of failing dataset has a corpus like the motivations. It's a very small corpus, right? 523 words. However, for the UNZA dataset, like the abstracts that students produce, look at this, 24,320 words. And true to that, if I say dspace vectorizer like this, and I say get feature names out, it would show me all the 24,320 words. In fact, there are so many that it won't show me everything here. Do you understand this? In fact, if you're working with very complex, I dare you, go and harvest all the posts from Zambian Watchdog and try and vectorize them. You have a lot of these, right? A lot of features like that. Anyways, so what we're saying is the fit and transform help us learn the model and to convert the text into numbers. And true to that, if I now check the UNZA IR here, and I say, I am interested in checking the very first element, but just a description. This is what I have, right? Now, I have morphological characterization was done, blah, 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 yada, yada, yada. It's some fancy stuff here. I don't know, probably in school of natural sciences and all that. If I check, right, my sparse matrix, this, sorry, not the vectorizer. If I check this sparse matrix under my data, and I say, show me what is on index 0. It's not going to show me everything here. But But it's going to show me for each one of these, because this is a lot, right? It's like it's an array that's going to have 24,320. They can't all be rendered here. It's like it's too much here, right? But in essence, for the vocabulary that I have, maybe if I do this is space to array. Again, it's not going to show me everything else. You know, list. You're going to have to do this. It's not working here. Yeah, I wanted to showcase everything. It's a lot of stuff. It's a lot of stuff here, but just do a list. I guess, yeah, you'd have to count this. I'm sure you can look them. You can look through these one at a time or something. How about to array, and then I say for var item. This is iterable, is it, in here? Yeah, print var item or something like that. Yeah, still, I mean, it's not showing me everything. I wanted to look through, but you can look through this at your own time to check. But it's the thing is so huge, right? It's like 24,000. Anyways, and then the metric shape is just going to showcase to you. In this particular case, it will showcase the number of documents in your corpus and the unique words. Is it? It's a tuple. It's a tuple, depending on where you're coming from. Again, just to kind of explain a bit more about the fit transform. It's an operation that involves two sub-operations. We're fitting and then we're transforming. So we're doing two things, is it? What the fit part of fit transform does is it helps you learn the vocabulary from all the documents. So in the case of the DSpace example, we are saying we're trawling through all of these, var, unza, ir, all of these documents. There are a lot, is it 2,000 documents? For each of the 2,000 documents, we are learning the vocabulary. What are the unique terms that we have in there? Right? Yeah. So in fact, what you can do is you can again get your vectorize and do a dot fit to do the same thing, right? And then you have to do another transform. So you fit it, you fit the vectorize, and then you transform it. But it's usually a lot easier. I like this myself, doing fit and transform in one go here. And the transform just converts each document into numbers, right? A bag of words in essence. It's like you're counting. Now, if we go back to this, if we go back to the vectorizer data, and we start checking maybe the second item, if we start checking maybe the second document, all zeros, I want to check if there's something that has at least all zeros, that has more than one term, right? If that makes sense, so that you could appreciate the fact that this thing just doesn't have ones and zeros, is it? It could be a bit more than that, but maybe it would be a lot easier if this is var student corpus or something. I'm looking for. I was ideally looking for something that has more than one term or something like that, but I can't see an example. I wanted to showcase to you that do not be deceived. Don't think that the way count vectorizer works is it just gives you ones and zeros. No, these are frequencies, counts. It's just unfortunate that most of these, unfortunate about computers and stuff. Maybe 203 or something. Corpus.iloc. I don't know if 200 and is it 203? I don't know if it's 203. No, appears twice here. So if I check 2003, if I come here and I say 2003, you notice here, beautiful. There's something that has 3 occurrences here. If you notice here, 3, there's 2, and then you have ones. There's a 2 here. Okay. Anyhow, so you have that, right? Fit transform, which is pretty straightforward. Again, we are wrapping it in. We are saying that the fit, learn what what words exist in your corpus. Transform will count these words for each document. Instead of you having multiple loops, you just use feed transform, right? Anyways, so that's that. Now, I think I mentioned this already. I highlighted the reason why count vectorizer returns a space matrix. It turns out that in most instances, right, when you're vectorizing this, when you're vectorizing documents, you will have a situation where a significant proportion of these words, if you look at this, most of them are 0, right? And because most of them are 0, the idea behind the space matrix is you save memory by just storing non-zero values. That's it, right? Now, in 2025 here, where we are using commodity computers that have this much compute here, you'd be like, I don't know about that, Lighton. But think of a situation where you're working with, billions, or let's just say millions of, like a corpus that has millions of documents. And your vocabulary is so huge, right? It turns out that this is helpful, from a compute perspective. These other slides here, which I'm just showcasing the things that I was talking about, like for you to be able to see what's in the space matrix, you use the 2-array method, right? Just use the 2-array method, and it will give you, observe, if I have this space matrix, and if I want to unbundle it, I'll just do a .2array, right? And then it's going to show me, of course, again, it's not going to show me everything, which is why I have these ellipses here, but it will give me an idea of the frequencies associated with each of the words in each document. And then from here, I can probably refer to a specific index, right? Like the last document, for instance, or document at index 10 or something, or document at index 200 or something like that, It's beautiful here. Okay, so we are returning we return a dense matrix by running the .2array method on the sparse matrix. Okay, now again, these slides are just explaining a bit more about if you want to check memory usage here, I have some code as well to help you appreciate, right? To appreciate why there's some saving, I guess, from a compute perspective if you're using a dense matrix versus using a sparse matrix, is it? Yeah. So at your own time, you probably want to, so you just do a .data.n bytes. You'll be able to gain a sense. Yeah, and I don't know if .data.n bytes .data, this thing has data. So .data.n bytes, and then I can compare this with this if I do a 2-array, a .2array, 2array .data.n bytes. Yeah, I don't know if you can see this. The sparse matrix for a student at risk of learning, at risk of failing, has this, is it? Sparse, dense. These are our sparse matrix. And then when we unbundle it, we have this. It's important for you to appreciate this, right? You end up being given a task and you're failing memory. I'm running out of memory when you're just using very brute force heuristics. Now, these are bytes, is it? But they taught you that kilobytes is going to be this divided by 1024, this divided by 1024, is it 1024? Right? We can see here our space matrix, it's up about 13.5 kilobytes of memory, whereas the dense matrix occupies 1 megabyte. You understand this? And really, if you look at our corpus, right, quite small. If we go back to our DSpace vectorizer data, and we say .data.n bytes, right? This is our sparse matrix. If we do .2array, right, .data.n bytes, look at that. So as you are scaling, it turns out that you require more compute. No. When you do this, when you start working on real world problems, right, what you begin to notice is you're running certain things and you have to wait. Like you're sitting there and you're waiting for this thing to execute in Google Colab or something. Maybe it takes 5 minutes or 10 minutes. This is the reason why it becomes important for you to go for approaches that are more optimal in terms of compute resources. But anyways, that's neither here nor there. Right, so the two array really converts your sparse matrix into a regular NumPy array, right? A dense representation of the sparse matrix here. It becomes useful when you're trying to inspect the result, right, of the vectorizer, like what I was showcasing here when I was indexing. When I was getting indexes like this. Say I want to see what is here, right? You've got to unbundle it. Anyways, but there's also, I showed you the get feature names out function. What I find it useful when I'm trying to concatenate the resulting count vectorizer, right? The dense matrix here to my original data frame. I like doing that myself, and so I'll use the get feature names out to do that. In essence, what I would do is I'll do something like this. Observe, I have the original data frame, which is this, right? What I want to do is I want to do this. I want to get this. I want to get this and stitch it to the data frame. So what I would do is I would say PD dot, I guess it's data frame or something, I think. And then I'll say, I want you to use the vectorizer dot get feature names like this and create a data frame, right? Create a data frame that is like this. You understand? So I'll typically use this to, and I've probably messed things up here slightly. Let me just change this to this var count vectorizer dot get feature names out or something. I've mixed things up slightly here. I've mixed things out slightly. Let me just fix this. Go back here. I think it is, but also just say like this: columns is equal to. Don't worry. I think there's examples in the. I think we've seen this as well. There's examples that you have in the examples that you have in the notebook that will explain this in great detail or something like that. Just go back here, and I don't know if it's columns. I've probably mixed up the keyworded parameters here. Just get count vectorizer dot get feature names out or something like that, right? So I'd mixed up the parameters. So what I like doing is I will create a vector like this. So this vector, it's a representation of all the 523 words. I've created a data frame, and because I've created a data frame, what I can then do is using this, I can say, because these are, if you notice, this is a 273 by 523 column, right? But what I want to do is I want to say I want to do a pd.concat, right? Concatenate the original student database, right? Concatenate this with this column wise, right? Column wise. I have, you know, I've done so many things in one step here, and I'm not really sure what. Let me just. I have this. I'm gonna call this var new df. This is why I hate doing this, right? And then I'm gonna say pd.concat like this, var student database, var new df axis is equal to 1. This should be able to work here. So if you notice, and see, I'm running out of C. I'll say var df fine or something like that. It's crazy here. If I do a column here, right? A dot column, what I'll have now is not the 69 columns that I have, but 592. Now it's 592 is there because, if you remember, the original data frame has 69, right? The dense vector has 523. The total is equal to 592. If this is making sense. I don't know if this is making sense. I don't know if it's making sense. Somebody was trying to call here. I don't know who calls. I don't know who calls on this time here. I don't know why this is. All right. I hope this is making sense here. Now it turns out that beyond this, can I just can I just join you just now? I do apologize here. Hello. Hello. Sorry about that, everybody. You know, sometimes I okay, I guess it's a Saturday or something. Yeah. Guess we have to switch off phones now. But you know, when you switch off phones here, again, also, it's like, no, he switches off phones. And you disturb the flow here. But so the get feature, you know, names out here tells you like every unique word in the count vectorizer. Crap, right? The interesting thing is that the order that you see, if you notice the var count vectorizer dot get feature names out, this order here, right? This matches the metrics that you see. So it's like if you spit out the very first document, right? The vector representation of the first document, the index at 1 is this. I mean, index at 0 is this. Index at 1 is this, which is why I'm able to stitch it together like that. And these are sorted by alphabetically also. If you notice, we are starting with numbers. Sorry about that. We are trying to zoom into here. We are starting with numbers at the top here, right? We start with numbers 1012, 2017, 2030, 5 years, 8th, able, A, right? A's, and then you start with the B's or something. So we are ordering these alphabetically. So these are ordered alphabetically, which is quite nice, right? I guess it makes it a lot easier for you to follow through with what's going on. Sorry, I'm trying to seek to the next slide here so that we kind of like follow with the flow here. Now it turns out, right, count vectorizer is quite powerful. You know, for instance, you can remove common words like stop words. You remember what we were doing, ladies and gentlemen? Well, we have got to first of all create a function that removes stop words. If you use count vectorizer, it does it for you. All you do is you use the parameter stop words. Observe, I'm going to come here and I'm going to create a vectorizer. But this time around, I'm going to call it count vectorizer stop words, right? And I'm going to feed it count vectorizer, and then I'm saying stop words is equal to English. Stop words is equal to English, like this. If I create this vectorizer, right, what's going to happen is if I, again, fit and transform, I've got to fit and transform here. If I fit and transform var student database, I've even forgotten what column this is. I'm going to come back here and just say var database dot column. It's this, is it? I've created this. If I do count vectorizer stop words, and then I do a dot fit, transform this. Transform var student database like this. I don't know if you've noticed this. The resulting sparse matrix has, and I'm going to call this again, var count vectorizer stop words data is equal to. Do you notice that the initial count vectorizer with data had a shape of 273, comma, this tuple that has 273 and 523, right? Words in your vocabulary. But the one I've created where I've removed stop words, yeah? This has the same number of observations, but we've drastically reduced the number of words in our dictionary. So we have 395. So in other words, we've removed all the stop words. And really, you know, if you're following through with what we're talking about here, if you check the size of the sparse matrix, the compute resources you're using up are significantly lower, which is one of the reasons, this is the motivation for why you're removing stop words or something like that, right? So anyways, you can remove stop words, right? Remove common words. But also, I've mentioned that this is quite complex what we're doing when you're working with text, is it? You'd be simplifying things if you assume that the task that you're working towards is going to look at words as individual tokens. I'm motivated for why in some instances you're able to derive interesting meaning when you combine words, right? University of Zambia. If I have a document that says University of Zambia, if I'm looking at those things as individual words, it will look at university as a single entity, over a single entity, Zambia as a single entity. But in actual fact, University of Zambia makes there's some semantic meaning associated with University of Zambia. So you can work with n-grams, right? N-grams are nothing more than contiguous sequence of n words. So if it's a unigram, it's a contiguous sequence of one word, right, from text, one word at a time. If it's bigrams, which is 2 grams, it's a contiguous sequence of 2 words, right? So in other words, computer science is seen as one entity. Learn programming, one entity. Light on Piri, one entity with bigrams, right? Kela Silanji, one entity or something. I don't know. And then with trigrams, it's a sequence of 3 words. It turns out that there are certain use cases where you're better off using a sequence of 3 words, not just unigrams, right? One word. So unigram, bigrams, trigrams, or n-grams, right? You can go on and on and on. Typically, though, for most documents that we tend to work with, text, at the very most, you probably end up at trigrams, right? A sequence of 3 words. Now, here's the thing, right? When you're using count vectorizer, the default behavior is you're working with unigrams, right? Surprise, surprise. Dot get feature. In fact, I'm going to look at stop words. Dot get feature out. Surprise, surprise. Look at this. Single words in your vocabulary. However, what you can do is you can explicitly tell count vectorizer that you want to work with bigrams only, in which case you'd have to instantiate, create an instance of count vectorizer such that you're feeding it n-gram range equal to 2,2. Right? Default is 1,1. You don't have to add this. If you leave it empty, default behavior is 1,1. 2,2 means you want to exclusively work with bigrams, right? In other words, if I come here and I create an instance of, this is the thing here, and I say, and I feed it n-gram range is equal to, it's a tuple, 2,2, and I want to mess up this, I'll just call this bigrams. When I fit and transform, again, when you create an instance, you have got to fit and transform, right? So fit transform, I'm going to say var, oh my God, the var, where is it? This. I should copy paste it somewhere. I'm going to copy this. And then I'm going to say bigram is equal to this. And then I'm going to say this bigram dot fit transform. I'm going to fit transform this. Observe. 1,396. If I gain, because it's sparse matrix, this is a 2 array to make life a lot easier. Don't want to create more things here. Or I'm going to say bigrams. I'm going to say dot get feature names out. And this thing won't show me, but it won't show me everything because it's a lot here. But observe, Zambian brand, like it's one thing. Zambia's plans, one thing. I don't know if this is making sense here. Anyways, so but you can also use, you can say, I'm going to combine unigrams and bigrams, right? 1,2. So in other words, you're telling count vectorizer to say, what I want you to do is create this sparse matrix that's going to have unigrams and bigrams, right? So you'll be Chela Silwanji. There'll also be a Chela, there will be a Silwanji. You understand? If there's a word that follows Chela Silwanji, a fourth year student, there'll be Silwanji A or fourth, because A is a stop word. Do you understand this? So I want to try this out, right? And just say, I'm going to say, I'll call this uni underbar bigrams, for instance. And I'll say this is going to be equal to, you know, this is the thing here. I'm going to say this is equal to 1,2, like this. I'll call uni underbar bigrams like this. And then I'll say this uni count underbar count vectorizer unigram like this. And I'll do a fit transform, right? The usual fit transform. You have got to do this every time you unfortunately, fit transform. I'm going to fit transform the same thing here. Observe. Now instead of 1,393, right? These are columns in your vector. You have 1,919 because what you're doing is you're combining unigrams and bigrams. If this is making sense, it gets even better, right? You can say, I want to do 1,3. This is ideal. I want to look at unigrams, bigrams, and trigrams so that I capture, if I'm working with a vocabulary, I'm using unigrams, bigrams, and trigrams so that I capture, look at this. My name is Tela Suwanj or something. I am a fourth year student or something like that. When you're capturing, if you're saying you're just going to work with unigrams, you just be capturing my name is separately. With bigrams, you're going to, or if you say 1,1 is the default configuration. My name is Taylor Suwanji. These are separate. 1,2, you're combining, you're going to have the same thing as what you have in 1,1, but you also be capturing my name is Chela Suwanji, Suwanji I, if you remove punctuations, I am MA, a fourth year student. Now some things don't make sense, but here's the thing, trigrams, right? I'm going to say, I want unigrams, I want bigrams, I want trigrams. This is what I'm going to do. And what I'll be capturing here is over and beyond 1,1 and 1,2, I'm going to be capturing as well things like my name is. And then I'll say, name is Chela, right? And then so my name is, and the name is Chela, and then is Chela Suwanji. Chela Suwanji I, right? You get the point. Anyway, it's okay, it's not okay, I don't know. Anyways, you can also control the vocabulary size, right? And you want to control the vocabulary size because look at this. This thing grows, right? As you're playing around with these hyperparameters, this thing is going to grow. So you want to be able to control this. Like for instance, you can limit to say, I just want to focus on the top 10 frequent words or something. Use the max features equal to 10. I'm going to let you play around with some of these things. It's going to be fun as you're working on your project, because over and beyond this, you should all be able to do this. But also you can filter, right? I mentioned this, like I want to remove words that appear in at least two documents. It's two documents here. Minimum df is equal to 2, right? Now I'm going to leave you with this. I'm looking at the time because also the person who was calling me here, they'll be like, where are you, Lighton, right? A relative thing here. There's a lot happening. An optimal configuration, if you've been following through, we start off with the default, right? Where we're saying you're just going to feed this count vectorizer, is it? Count vectorizer, I'll call default. Oh man, count vectorizer default is equal to just count vectorizer like this. This works quite all right, but you're not really going to build, you're not going to learn a model that is effective like this, right? What you do is you have got to use these different parameters I was talking about. Like for instance, you say stop words, right? Is equal to English, like this. Comma, you can specify features, n-gram range, right? So you do a combination of these. The default is lowercase is true here. Say convert to lowercase, something like that. Anyways, listen, I'm going to pause here and ask if there are any questions. This now, what we've discussed so far, is good enough for all of us to work on our chosen topics. Are there any questions about count vectorizer? I hope you weren't thinking that we are going to have to do an implementation of the bag of words mode or something. No. Okay. If there are no questions, I'm going to leave you with that. There are never questions. What is this saying time? What is that? I don't know what time is it. Yeah, Moses. I mean, you know, Moses, while you're, where are you going? Are you going partying or something like that? Okay. I've taken note of the time, Mr. Moses. Thanks, guys. See you tomorrow. We have class at 18. I want us to get TF-IDF out of the way. Bye.